Okay, so let's talk about this assignment on implementing symbol table abstract data type using C programming language. And this is an introductory video that can help you get started with the program. The goal of the assignment is for you to learn C dynamic memory management tools such as how to allocate memory using malloc, or how to allocate memory for an array of things using calloc, how to reallocate memory, and also how to free memory that was allocated. Also, understanding how to create abstract data types like a symbol table and create objects of that data type. We're going to continue to understand how to use GDB to debug our code, and we are also introducing this idea of a makefile that will allow you to manage this project in a more efficient way. Some background information. Select a symbol table is a collection of bindings. Each binding has a key and a value. In our context, key is a string that will uniquely identify a binding. A value is some data pertinent to its key. In our context, the value would be provided by the client. So we would assume that the value would be a void star, which is some generic data type that we will associate with the key. There are many applications of symbol tables, and you can study them as you take more computer science classes. So the first part of your assignment is for you to implement a symbol table using a linked list. In other words, we store symbol table data records in a linked list. So keys and values are stored in a linked list, and you have to traverse the linked list to add, update, or delete these key value pairs. We expect the linked list to have linear time performance, as one must traverse through the linked list to add, update, and delete these key value pairs. Highly recommend that you look at some of the references to find additional help in completing. Now let's take a look at a conceptual view of a linked list implementation of a symbol table. We recommend that we think of a picture like this. We have a pointer that is a pointer to one of the records, a header record for the symbol table, that contains a pointer that contains two fields. One is a pointer to this linked list, and the other one is the size of this linked list. So the pointer to the linked list points to the first record of the symbol table. We implement a symbol table as a linked list, so a linked list node contains three fields. One is a key, a value, and a pointer to the next record. And the linked list ends with a null pointer. All this memory is going to be allocated in the heap using malloc. This memory, just of one single variable, will be on the runtime stack. So this is the conceptual view of symbol table. In terms of using something like this, we may assume that we have a function called symbol table new, which gives us a new symbol table, and then we can put into that symbol table this value and this key and this value. So key and a value and so on. So if you really think about this, this is an address of an area that contains a pointer to the string Gita. So Gita is not stored here, but it contains a pointer to some other location where the Gita is stored. Same thing is true here. This field is provided by the client. The client will give you a pointer to some generic data type, which we wouldn't know at the time we developed this symbol table. So we ask the client to manage the memory associated with the value, but we're going to manage the memory associated with the key. In other words, when a key is provided, we're going to make a copy of that key and store it and put a pointer to that key. So that's the first part of the implementation, symbol table linked list implementation. One of the problems with this implementation is that to add, update, delete records, you may have to traverse the entire list, and that can take linear time. So in the second assignment, in the second implementation, we're going to try to fix that using a hash table implementation. So let's start with the linked list implementation of the symbol table. It is up to you to design these symbol table data structures. And the goal of this video is, or goal of this part is to show you how to think about designing and implementing just a linked list implementation. And so we hope that you would learn some of the things that are important and apply to your symbol table design. So in this case, we have a .h file called linklist.h, which contains some of the functions required for our generic linked list class. So linked list T is a pointer to a struct linked list. So we're defining alias for a type called linked list underscore T, which is a pointer to a struct linked list, which is to be defined later. We have functions like linked list new, which will return a new linked list object, and then linked list free, which will free all the memory associated with the old linked list. Make a note that in the .h file, we are writing what the function does using the name of the arguments itself. So there are a number of other things like get length and add last to the linked list given an item. So in this case, we're going to try to design a linked list of strings. So let's take a look at some of the conceptual things we need to understand. So here's the sort of design of this generic linked list, which contains a my linked list would be a specific instance of the linked list underscore T. As you can see, my linked list is just a pointer to a struct linked list. And a struct linked list in my design would contain a field which is a pointer to a linked list node. You can consider this as the head of the linked list, and we can include other fields that can help with the linked list structure. Each node contains two fields in my design. A p item, which is a pointer to a string. Those things have to be allocated. So this would be a char star, and this would be just a pointer to another struct node. Now, in terms of implementing this structure, we can think of something of this form. So where we have, so let's take a look at this here. So this is the implementation file of the linked list.h. In this case, we include the linked list.h in the linked list.c file. This is the linked list.c file. And here we have defined a struct node, which is of this form. The first field is a char star, and the second field is a pointer to another struct node. Then we have struct linked list, which is this form here, which contains a head pointer, which is called phead. That's a pointer to one of these struct nodes. So that's the design we will use to demonstrate how to come up with a linked list implementation. We'll show you one or two functions, and then you'll be responsible for developing the other functions. Let's first think about how to create a new linked list structure object. So linked list new, it would be a function that gives you that structure. It returns a pointer to a struct linked list, which is we call the type linked list underscore T. So what do we need to do? First, we need to allocate memory enough to hold a struct linked list. So we take the size of struct linked list and allocate memory. Now, keep in mind that you have to typecast, since malloc returns void star, you need to typecast that to be a linked list underscore T type, which is a pointer to the same pointer type as plist. Assert that you received enough memory to do that. Plist had to be not null, so that you can dereference plist to look at the phead. So plist arrow phead is this pointer here, and we make it go to null, and we return the plist. So essentially by calling after you call linked list new, you had created this structure here, but you haven't added nodes yet. So we'll talk about adding nodes next. Now let's think about writing a function that will add any new item as the last element of the linked list. So you're given a linked list object and some new item, p item, which is a string. So now we have 2 pointers that will help us do this. You assert that the linked list is not null and the item is not null. If the linked list is not null, then we'll be able to look at the head of the list. So assume that we don't have any nodes in there yet. So temp would be o_list arrow p head. So which would be pointing to this field here. That's the one you're referring to as temp now. It says while temp is not null. So in this case, if you don't have any nodes yet, temp would be null. You don't even go into this loop here. Now you're going to create a new node, which is a malloc, the size of struct node. So let's allocate a malloc for this. Let's allocate enough memory for this node. And make sure that the new node has received the memory. And then we can do new node arrow p item would be, now we need to allocate memory to copy Bob into that. So we are given Bob, we're going to make a deep copy. So we have to allocate memory with the string length of p item. So Bob would be, that's 3 plus 1. So we allocate 4 bytes to hold Bob. That's the new node p item. So that's a pointer that's given to us. And then now you have to copy. These 2 steps are really important. You allocate memory and then copy the item into that field. Now we make sure new node arrow p next, which is this pointer here, would be null. And now temp is null, so we assume that this is the first node we're going to be doing. So if temp is null, then we say o_linked arrow p head, which is pointing to this location here. That would be assigned the new node, which is the address of this new node. And that's how you do the first node. Suppose now we have inserted Bob. We're going to insert Sophie as the last item. So we are sending Sophie, and we want to add as Sophie as the last item. Again, you go through all of these things. Now let's think about what happens here. So we start by saying temp is assigned p linked list arrow p head, which means temp is actually pointing to the first element of the list, which is in this case Bob, is the first node. Temp is not null, this is not null, and temp arrow p next is not null. In this case, temp arrow p next would be null because we only have one element here. This node is called temp. Temp arrow next would be null. So therefore, it doesn't go into the loop. But if it does, what it does is to really keep looking until you find the last node. The way you know that you found the last node is by looking at the next pointer and saying temp arrow p next is null, then we found the last node. Just like before, we allocate memory to hold a string, hold a structure. So we create a structure first, and then we make sure that's not null, and then we do the same things we did before. Now we have to create memory to hold Sophie and copy Sophie, which was given as p item, into that location. So we have a pointer to that memory that was allocated. We make the new node p next to be null, and then we insert, if temp is null, which is not the case, so temp would be pointing here in this case. So what we're going to do is we're going to say temp arrow p next, which talks about this pointer here. It's allocating, it's pointing to the new node. So essentially temp, after we come out of this loop, would be the last node, and then we insert the new node as the new last node now. So that shows you how you can implement add last function. We'll test this function as we go and test the memory and other things that are important to test. Now let's talk about how to free a list. We know how to insert a node to a list. So to free a list, if you think about a list like this, free a list you need to free all the memory you allocated for the strings, and then you have to free all the nodes, and then finally you have to free this. So if you free the entire list, the only thing left would be this variable that is on the stack. Everything else is going to be gone, this and this and this. One thing that's very important is that when you free the list, you have to make sure that you don't free a node until you have saved a pointer to the next node. Because in case if you free this entire node, you're going to lose a pointer that tells you where the next node is. So if you're going to free the list, then you have to know what the next pointer is, save a copy of it, and then free this node. And so by going through the list, you can free all the nodes one at a time, and then come back and free the structure that was the linked list structure, and then you're done. To make things a little bit easier for us, here I have defined a function called a static void function called linked list free node. Now it's static because it's only supposed to be a helper function. What this function will do is to take a p node as an argument, a pointer to a struct node, which is of this type. That means one of the addresses of one of these nodes as an argument and try to free it. So the process is not difficult because what you need to do is first of all free the item associated with the node. If you recall, in our add last function, we have to allocate memory for this. So we are freeing that first, and then we are freeing the p node. Now note that when you say p node arrow item, when you're freeing this, you're freeing the memory associated with that location, p node arrow item. When you say free p node, you're not freeing p node, you're freeing the p node, the memory associated with free node. So if you recall, we had two calls to allocate a structure and then allocate memory for the string. And now we have two free calls to match that, to remove the memory associated with the string and then remove the structure. Now we're not going to write the next function, which is the linked list free, which will free the entire list. As I said before, your logic would be to go through the list one by one. As you go, make sure you save a pointer to the next node and free, then you can call the free node on this one and then continue to move forward until all the nodes are gone, and then come back and do the free this structure, and then you have completely freed the memory that you allocated. So one thing we will look at when we are testing this is that if you do any number of mallocs, you must have matching number of frees to make sure that you have freed all the memory that you have. Now that you have seen how we implemented a linked list of nodes whose items are strings, I think you're ready to do the symbol table implementation using linked list. So create a .h file using the functions that are defined here, and then start defining your data structures for symbol table underscore t, data structure for your nodes, and other things you need, and start implementing these functions. Once you do that, we will talk about in the next part of the video, we'll talk about the hash table implementation of the same interface. All right, so the next part of the assignment is going to be implementation of the symbol table using a hash table idea. So we want to implement a symbol table as a hash table. In this concept, the keys and values are stored in buckets. Each key, we can apply the hash function to each key, and that can determine the bucket value. So each key maps to a bucket based on the hash function. Each bucket has a linked list that stores all the keys that maps to the same bucket. It is possible that two keys, when you apply the hash function, will map to the same bucket. In that case, we will create a linked list from that bucket to attach those two keys and values that have collisions. So that's the idea. There are some references here that you can take a look. So here's a picture, a conceptual view of what you may want to do. Like before, you have a variable called on the stack symbol table or symbol table variable, which points to a symbol table header structure that points to an array of linked lists. So this is what we need to do. So we have the number of elements in the symbol table, which is 1, 2, 3, 4, and the number of buckets in the symbol table, which is 5 or 9. We want to implement this structure so that we can expand this without having to limit the number of buckets that we have. So in other words, this has to be a dynamic array. That is very, very important. So before we go into that, to understand how to do it, let's do a simpler version of it. So here's a simpler idea of array of linked list. You have a variable, myArray of linked list, which is a pointer to a structure. And in the structure, you have maybe one or more fields. One field called the array. The array points to a dynamic array of linked list. And each linked list item is one of these struct nodes. And what we're going to do is to write the code to implement the structure and see how that works. So now let's think about how we're going to do our array of linked list idea. Now this array of linked list, each location is a linked list by itself. It's really not a simple static array. It has to be a dynamic array. So we have to define our data structures such that this becomes a dynamic array, and we will allocate memory at runtime for this array, and then we will allocate nodes at runtime. So to show a mapping between these two, the picture and the actual code, here we have the struct node as before. This is one of these things. And then we have a struct array of linked list, which is a double pointer. So it's a pointer, so we have a field called array. It's an array of struct node stars. So you can think of one star as an array. Think about this as an array. So it's whose elements are struct node stars. So when you define like this, a double star is essentially the name array, means that if you dereference it once, you get to this, and then if you dereference it again, you're going to get to the linked list. So essentially, if you take array of 0, which gives you the beginning of the list that starts from the bucket 0, and then array of 1 would be the beginning of the list that starts from bucket 1. So now let's go over some of the steps that are necessary to create a structure like this. There can be multiple ways of doing this, but I'm going to demonstrate to you one way of doing it. But we take a very organized step-by-step approach to this. So my approach would be to create one of these structures first, and then create the array, and then start adding nodes to it. So this function called array of linked list new, what it's supposed to do is to create the structure, and then create this dynamic array, and then return that to the program. And so that's going to return that. And then when we do the operations, like when you do functions like add first or add last, we'll think about how we add the rest of it. So right now, I'm just going to show you this and this part of it. Okay, so in order to create one of these things, what I need to do is to have an object or a variable called array of ll underscore t, which, as we know, it's a pointer to an array of linked list, which is given here. And let's call this new array. Let's call this new array of linked list. So this is one of the variables I have, which is a pointer to struct array of linked list. And so what I need to do next is to allocate memory for this block. So I'm going to say a new array of LL is equal to, so let's do a malloc. So we do malloc size of, and what we want to do is the size of this block. So it's going to be size of struct array array of LL. So that gives us the block. And then in order to typecast, you want to typecast this to be an array of LL underscore T, which is really a pointer to an array. So let me extend this a little bit here. Okay. So now what we need to do is the following. So we created the structure here, this structure here. So now we need to create an array to hold that. So, but before that, we must assert that the new array of LL is not equal to null. Make sure that's we were given this block of memory. This is the block of memory we asked for. And now we have to allocate memory for this block here. It's the array. And I'm going to allocate this for this field. So what I'm going to do is I'm going to say new array of LL arrow array, which refers to this field here. It's going to be assigned. It's going to be assigned malloc. Actually, I'm going to use calloc because I want to do an array. So I'm going to assign an array of this size, and whose each element is size of struct node star. So let's think about what we did so far. So you call the calloc. Calloc gives you this block of memory initialized to each one, where each one is a pointer. It's a struct node star. Each one is a pointer to one of these things. So we do allocate memory for that. Now this size was in the assignment it would be 509, but I put a 100 here just for demonstration purposes. The next thing you want to do is to make sure that we can assert this block. So we can say assert new array of LL is not null. And then if it's true, then return if it's fine. If it's not null, then return a new array of LL. So that's pretty much what we will do in terms of writing the array of LL new function. So now let's think about how we write another function called array of LL at first. In this demonstration, I'm given an array of LL object and an item which is a string and an index. In the assignment, this may be the index you get from your hash function. And so what we're going to do is to add this item, a node that containing this item, to the beginning of the list that starts from this bucket index. So how do we go about doing this? So let me have a few things here before we start. So let me have a pointer called new node, which is I'm going to use that to create a new node to add this to as the first of the bucket index. So we will do two assert statements. We will assert that O array of LL is not equal to null. And then also we will assert that the P item is not equal to null. P item is not equal to null. And so the next thing I would do is to call malloc some amount of memory. So let's say malloc size of struct node. Size of struct node. Let's see what we did there. So essentially, I'm trying to get a node allocated. So one of these nodes allocated to work with. So now let's see what the next steps are. Obviously, we want to make sure that we typecast this to be a struct node star. All right, so we requested memory. Let's assert that a new node is has a valid location. So assert that new node is not equal to null. And then we are going to, so now that we have a node, we can say new node, arrow, p item. P item is equal to, let's malloc enough space necessary to, so let's take the string length of the p item and add 1 to it, and that's how many bytes I need to malloc. And then I will typecast this to be a char star. And so I allocated memory for the new node, which indicates that I did the following. I allocated memory for, say, Bob. And so now I need to copy the Bob into that location. So we're going to do string copy. So the next thing we're going to do is we're going to do a string copy, take the new node, arrow p item, and a string copy the item that's given to you. So this will make sure you make a defensive copy of the string. And then now we are ready to insert. So insert to the beginning of the list. So we know the beginning of the list is called the array of index. So we'll have to insert it to that location. Now, before that, so now that we have created a node, what I'm going to do is I'm going to make to make it go to the beginning of the list. Say, for example, we had Sophie, and now the Bob is coming in. So I need to make sure that the new node next pointer will go to the existing beginning of the list. And then the beginning of the list will become the new node becomes the beginning of the list. So that's what we're going to do. So how do we do that? So we take new node, arrow p next, which indicates the next pointer, should point to the beginning, the current beginning of the list. We talked about the current beginning of the list as O array of LL. Arrow array. This gives you access to this array, and that's what we get. O array. This is the object. We have O array of LL, which is a pointer to one of these things. We get to the field, and then we look at the index. So this part would be, so what's on the right hand side is now a struct node star. So it's a pointer to a struct. And so we make the new node next pointer go to that, and then the next line would be O array of LL arrow array, which talks about this pointer here, because we have a pointer to this, that's the array of LL. We use that to get to the field array, and then we dereference and get to the index field, which points to the beginning of the list, and that's going to be the new node. So essentially what we have done is to insert the new node into the array. Now if you're successful, you can return 1 to indicate the success. And so that shows the code for adding a new node into the beginning of a list, starting at the bucket of index. Now let's take a look at some code that, now that we developed two functions, array of linked list new and add first, and this code will demonstrate how to use it. So suppose I define a variable called myArray of LL, which is of array of type that. And essentially, that's the variable that I'm declaring. It's going to be on the stack, this variable, which is a pointer to an array of LLT. And now, the next thing I'm going to do is I'm going to call the function that we developed called array of linked list new, which is supposed to give me a structure as we discussed. It's going to give me this structure and this structure here. And then I'm going to call the function add first, to add to that object the string guna at bucket 0, bucket rt at bucket 0, bob at bucket 1, guna at bucket 1. Now note that in this case, we are not looking for any kind of duplicate. Duplicates are supported, and unlike in the hash table, the key is unique. So we don't, in this case, we don't have to, we're not looking for that duplicate. So my goal is to really show you, use the GDB to show you how this is going to work. In other words, is my new function is working? Is my add first function working? So we can look at that using GDB. So to use the GDB, let's do the following. We're going to compile this. We're going to compile this using the -g flag, and then I'm going to start Emacs. And now, as you know, you press Escape X, then you type GDB, press Enter, and note that the array of LL. So I'm going to press Enter, and then what I like to do is to put a breakpoint at 1, which is the main function, and then type run. And now here we are starting the process. So let's see what happens right now. So we have declared a variable called new array of LL. Now I'm able to print this using in the debugger. So let's look at new array of LL. What does that mean? It is a variable. It's not been initialized to any memory yet. Now then we call malloc here, and this is supposed to give you some valid location. So if you say next, you'll go to the next line. So at this point, we assume that this new array of LL is now initialized. So if you print p new array of LL, now note that it has a valid location now. So it's no longer null pointer that we cannot dereference. Now it has a location that we can dereference. We assert it, it's not null, so they should go through to the next step. Then now we are asking, at this point, we have the picture. If you look at the picture, what we have is this thing here. But this would still be null because we didn't really put anything into that. So in fact, we can look at it and say, okay, now that we have a new array of LL, so let's try to print new array of LL, and then arrow array. If you print that, you notice that this was null. The field is null. So therefore, we need to allocate some memory for that. So what we're going to do is we're going to allocate this much memory for that. So let's go to the next step. So now we have allocated memory. So at this point, if you print new array of LL, arrow array, so now you'll see that there's some memory that was allocated for it. Now you can see some closeness here. These are all coming from heap. So these are heap addresses that you're seeing here. Now we assert it's not null, so we should see that clearly. And if you print the size of new array of LL arrow array, so what you get is 8 because it's a pointer. But we know we allocated size times 8 bytes in there. So this is a pointer, so you get that. So let's go to the next step. And the next step, so in the new function, next. Okay, now we're back in this function here. Now, I can either step into the add first function or I can just bypass that. So if I type n, I will bypass. So at this point, I would assume that my structure, so if I print my array of LL, arrow array, so you look at the arrow array of 0. Now this refers to the let's take a look at the picture here. So this refers to this location here. But if I want to look at the item that was placed in, which I assume would be guna, you should see guna. So in order to see that, then I'm going to type arrow p item. So it seems fine, right? And then let's print next. Now we must have placed RT in there. So if I do the same thing, my array of LL, arrow array of 0, arrow p item, and you see RT. Now, if I want to see guna, obviously guna is the second node now. So if I want to see guna, then what I need to do is print my array of LL, arrow array of 0, array of 0 here. So that gets you the 0 things. Then if I want to go to the second node, I would use the p next, which refer to the second node, and then look at the p item in the second node. In that case, it's guna. It shows you where this string is stored and other information. So it's a simple debugging session. As you can see, when you're debugging, you can go through the entire structure by using pointers and dereferencing to see what's going on. Is it doing the things that you expect the code to? So finally, to wrap things up, let's talk about some of the common things that you may run into in this program. One of the most frustrating and difficult thing in this program is finding the DMM or dynamic memory management bugs. So there are a few things that you can do to simplify things a little bit. So we can diagnose seg faults using GDB. So for instance, well, first of all, look for common bugs, such as that here you have a pointer, but you're trying to dereference without allocating memory for that pointer, and so on. Now, so look for some of those common bugs. They are in the lecture 8 on data structures plus debugging. So diagnose seg faults using GDB. You can, when the seg fault happens, you can issue the command where, and you can find out where the seg fault happens. Maybe line may not be the place where the error resides. You can manually inspect malloc calls to see that if the malloc calls allocates enough memory. Like for example, this should be string length of S1 plus 1. You need 1 byte more than the string length of S1 to do it. So just inspect those malloc calls to make sure that you're doing it. Like for example, perhaps what you need here is a long double. Instead, you are doing long double star, which is just a pointer. And if you think you're not allocating enough memory, you can hard code some, each malloc you can say, give me 10,000 bytes. And if the error disappears, then you know that at least one of your calls is requesting too few bytes. And you can incrementally restore each call to the previous form. And the other thing you can do is if you think that your free calls are causing the problem, you can slowly comment out the free call, maybe freeing memory that's already been freed or freeing memory that should not be freed, such as a variable that's in the stack. You cannot free that. Or freeing memory too soon and trying to dereference that. So those are some of the things that can go wrong. So again, you can incrementally comment in each call of free to figure out what the problem is. Then finally use meminfo and valgrind. They can give you good clues as to where the memory leaks are, and then you can go look for those lines and fix them. So they're all useful tools. So expect to spend some time debugging, finding memory bugs, because this program does a lot of mallocs and callocs and free, and you have to make sure that all the mallocs are covered by a free somewhere in your code. Good luck with the program.